Welcome. So we have two different ways of solving for electric potential. So this is going to be the superposition of known electric potentials, sometimes called the sum of dV's method or superposition method. So in this sketch organize solve, we're going to start by sketching, and we want to draw our charge distribution as simply as possible. And again, what we want to do is we want to reduce dimensions as much as we can. In this case, we're going to think of a semi-hollow disk. So we're going to think of a disk that has a center, but otherwise is filled in. And we want to consider, a point along the center of this disk. So in this case, we can't make it 0 or 1 dimensional, but we can make it 2 dimensional. So that's as simple as we can. And then what we want to do is we want to choose a constituent shape. And this is what we're going to be building our disk out of. So if we have a 1-dimensional distribution, we want to make it out of objects 1 dimension less than our charge distribution, which would be point particles. If we have a 2-dimensional distribution, then we want to make it out of something with 1 less dimension than 2 dimensions, which is going to be 1D. So that's going to be a 1D line, arc, or ring. And once we have this constituent shape, we want to show what this constituent shape is by drawing two constituent shapes in the distribution. If we're doing point particles, we'll often represent these as slices. If we're doing 1-dimensional things, we can usually just draw the actual thing in a little bit. So I could draw this as a ring, but my ring has to have some arbitrary thickness to build it as this, and then I can build another one as we're doing on this. And so as we draw these constituent shapes, then we want to draw our little r vector for point particles and the relevant measure for others from the slices to the point in question. So I can draw all the way from here to here as a kind of r vector. What's really important for each of these individual slices is in fact just the z dimension. And then once we have this, we want to establish a coordinate system aligned with the problem. So in this case, we would probably want to use cylindrical polar coordinates as we do this. So in our organized step, what we were saying is the electric potential of the distribution is equal to the sum of the electric potentials of all the pieces, or the integral of the electric potential of all the pieces. So if we have a discrete set, then we can look at the differential electric potential of a point is going to be 1 over 4 pi epsilon naught dq over r. And what's really nice is, of course, we don't have to worry about the r hat like we did. And so we can also take a look at, since we're making this of rings, the dV of a ring is 1 over 4 pi epsilon naught z dq over, in this case, z squared plus the two-dimensional radius squared to the 1/2 power. So what's really important for this is mainly the definition of q. So q for a point particle is just q. Awesome, we did it. But we also have the q of a one-dimensional point particle is going to be lambda dl, where dl is dx, dy, or dz for straight lines, and dl is r times d theta for arcs and rings. And then if we have a two-dimensional shape, it's going to be eta dA. Some other books use sigma dA. This is my charge density per unit area, and dA is equal to the length times the differential width for a rectangle. And my dA is 2 pi times the two-dimensional radius times the d of the two-dimensional radius for a circle. So when I am solving this, I would then have, right, for discrete particles, if I'm summing up individual discrete ones, right, find V of each piece, and my V is the sum of the individual V's. That's not super interesting, not super useful, or I guess a little bit trivial, I guess. For our continuous, now our V is our integral of dV. So we've already found what the dV is, whether we're summing up points to make a one-dimensional distribution, whether we're summing up rings. If we have another, right, thing to do other than a ring, if we have lines or anything like that, we will use the differential equation for that in finding the dq for these. So we have then that our integral, we want to find the bounds. Perform the integral, and then simplify using algebra, and of course evaluate bounds. So we'll find another way to do this, but this is if we want to add all of these. And we'll find that it's very, very similar to what we did for electric fields, but in fact quite a bit easier because we don't have this direction to worry about anymore. So that's why we can do all of this in just one SOS video.